This presentation shows the results of two computer models used to reveal airflow patterns in a generic indoor space. The space is set up like a classroom with the desks, occupants, and a standing mannequin at the front of the room. The space is large enough to accommodate 20 desks, but is set up with half the total number of mannequins, with each occupant separated by 6 feet, approximately 2 meters. The room dimensions are 30 feet wide by 20 feet front to rear, with a 10-foot high ceiling. Air is let into the room through 4 uniformly spaced diffusers in the ceiling, the small squares. Air is exhausted through one rectangular grill also mounted in the ceiling, similar to that seen in this photo. Although set up like a classroom, it can be imagined as a conference room, business office, restaurant, or other commercial enterprise where people gather. Each mannequin has a small zone on the front side of the head from which air and particles are discharged into the space to simulate breathing, specifically the exhalation part of that cycle. Although exhaled aerosols are composed of a wide range of wet particles, typically from 0.1 micron, 100 nanometers, up to over 100 microns, depending on where the discharge falls in the range from restful breathing to coughing and sneezing. To simplify modeling, only 2 particle sizes were included, 3 micron blue particles and 50 micron red particles. Particles below 20 micron are easily entrained in moving air, so the 3 micron size is used to represent the group that would remain suspended. Particles above 50 micron are likely to assume parabolic trajectories and fall to a nearby surface. In the range from 3 to 50 microns, particles can remain suspended for long durations and be deposited long distances from the discharge point based on local flow rates. Injected particles are treated as inert spherical particles with a specific gravity of 1.4. Particles do not undergo further desiccation, attrition, or agglomeration in the model space. In the first video clip, both particle sizes are injected from student 24, second row, fourth from the left side. For simplification, the discharge stream is continuous rather than pulsed as would occur in a typical breathing cycle. The discharge rate is equivalent to a person engaged in an active discussion. Note that the initial upward movement of discharged particles is due to thermal effects that lift the warm 92 degree Fahrenheit, 33 C, discharge in the cooler room air at 65 degrees, or 18 C. For this initial simulation, the room ventilation system is not activated. That is, there is no air flowing into or out of the space through the ceiling-mounted diffusers and grill. Air movement in the space is due to the thermal effects from the mannequin surfaces that are set to 85 degrees Fahrenheit, 29 degrees C. This model setup demonstrates how the 2 size classes act in an essentially quiescent environment. As expected, the smaller blue particles remain suspended and wander about the room on the thermal currents. The larger red particles, with a suspension velocity of about 1/3 foot per second, fall quickly to the desk and area surrounding student 24 in the virtually still air. This demonstration represents about 5 minutes of real time. The second simulation uses the conventional top-down mixed ventilation system with air admitted into the room through 4 uniformly placed ceiling diffusers and exhausted through one ceiling-mounted rectangular grill. Air is admitted into the space at a change rate of 8.5, with diffuser exit velocities of 170 feet per minute at a 20 degree down angle and a temperature of 65 degrees Fahrenheit, 18 C. Following establishment of the steady-state airflow distribution, injections began from student 24 and ran for approximately 1 minute real time. The strong flow currents are evident by the rope-like structures that lift both classes of particles up and away from the source. The smaller blue particles are more widely distributed than the larger red particles that have been carried away from the source and deposited on the floor near one of the adjacent mannequins. Injections for the remaining mannequins also demonstrated the strong flow currents across the space. In about 6 minutes of real time, the entire space is filled with particles. At that time, the injections were stopped, but the air continued at the same flow rate to demonstrate the exponential nature of purging a space. Note that red particles have been deposited on the floor across the room, as well as a significant amount deposited on desktops. These simulations should provide insight for the general public concerning the movement of hazardous particles in indoor spaces. It is clear from these models that no amount of social distancing is adequate to prevent inhalation of harmful particles in spaces with conventional top-down mixing ventilation, the most common type of HVAC system installed in the United States. It should also be clear that no amount of system cleaning, balancing, flow adjustment, or air treatments would change the basic internal flow dynamics set up by the ventilation system. Note also these simulations use the equivalent of 100% fresh air, that is, no particles entered the space with the ventilation air. In conclusion, reducing indoor hazards, both biological and chemical, would require a revolution in ventilation practices that changes the top-down mixing system to something that moves the air uniformly through the space, with reduced mixing and recirculation. For more insight, contact an internal flow specialist to evaluate your indoor space.